العالمين.
All right, so to recap, we've kind of taken a sidestep with linked lists. Like we have this dynamism now where we can grow and shrink our chunks of memory without over-allocating or accidentally under-allocating, as in the world of an array. We don't have to worry about copying values endlessly, because once you allocate the node, it can just stay wherever it is in memory, and you can just maintain, you can just stitch it together somehow. But unfortunately, we've sacrificed what we started the class with in week 0, which was like binary search, divide and conquer, which was like gave us that log n running time, which was really compelling if you think back to the demonstrations and the visuals. Can we get the best of both worlds? Can we get the sort of speed of binary search, something logarithmic, but the dynamism of something like a linked list? Well, we can actually, I think, if we start to think not in a single dimension, just the x-axis, if you will, but 2 dimensions, such that our data structures can maybe now have width and height, if you will. And so a tree is perhaps the right term here, much like a family tree. If you have sort of your elders up here in the tree and then the branches below them for their children and grandchildren and the like, that's actually what a computer scientist means when they talk about trees. Not a tree that grows up like this, but really one that typically is depicted growing down, although this is just an artist's depiction no matter what. But there are certain types of trees in the world called binary search trees that are structured on paper and visually like a family tree, but they have a special property that lends themselves to exactly that feature, binary search. So for instance, here is an array back from week 2, and I've sorted a whole bunch of numbers herein from 1 to 7. We know we can do binary search on this structure if it's implemented as an array, but what feature do arrays, to be clear, not have that linked lists do? Today's kind of a seesaw. Like, what did we just gain by adding linked lists that arrays do not allow? Yeah. Yeah, you can insert more elements without having to copy or moving everything else around. Like right now in this single dimension, if these values to the left and or right are already used, then you have to move everything. And that's where we started today's story. So arrays kind of paint you into a corner because you have to, by definition, decide in advance how big they are. Well, couldn't we have some kind of array that can still grow but still is contiguous so we can do binary search in some way? Well, yes, if we sort of rethink how we implement binary search. Let me propose that I've chosen these 7 elements in the array, much like the lockers from week 2, to be ordered from smallest to largest. I've highlighted now in yellow the middle elements here. And if we were telling the story of week 2 going left or going right, let me highlight in red the middle elements of the left half and the right half. And then let me further highlight in green the other elements in between those. And there's actually a pattern here, as you might notice, whereby there's 1 yellow in the middle, and then there's the 2 red and the 4 green. There's kind of an implicit structure there, if you will. And what if I do start to think in 2 dimensions, and instead of laying out an array of lockers like this on the x-axis only, what if I kind of like slide the 4 up and pull the 1, the 3, the 5 down, and kind of draw this in 2 dimensions instead? Well, let me do that as by separating these things like this, such that now let me propose that each of these squares, maybe it doesn't have to be contiguous. It can be anywhere in the computer's memory. But I can't have these crazy gaps among them. How could I perhaps keep these things connected conceptually? What should I add to the picture, if you will? Yeah. Say again? So branches, metaphorically here, and more technically in the language of C, maybe just some arrows, some pointers. So I won't bother drawing things as rectangles constantly. Let me propose that we're now just abstracting away what a node is. But let me claim that each of these squares now is a node. And a node might have a number, but it might also have a pointer. Heck, maybe even 2 or more pointers. And let me draw those now. I don't care about addresses like 0x1, 2, 3, 4, 5, 6, 7, 8, 9 anymore. Let's just draw our pointers with arrows. But now let me propose that we could very well think about this as a tree storing what was previously array data, but now each of these nodes can be anywhere in memory. And moreover, even though I've kind of painted myself into a corner visually on the screen, so long as there's more memory in the computer, I could put the number 0 over here. I could put the number 8 over here. And if I'm smart, I could probably, if I want to insert other numbers like 2.5 or 1.5 or values in between, I bet we could kind of make room by swiveling things around and just kind of hanging things off of these branches slightly differently. And so what does this gain me? Well, if I instead start to model my data, not single dimensionally, but in 2 dimensions, and I connect those nodes with these pointers, what can I now do? I think I just gave myself back binary search. Why? Suppose I'm searching for the number 5. How do I find it? Well, just like in a family tree where you might visually start reading from top to bottom, I'm always going to start from the so-called root of a binary search tree. This is just like the list pointer that kicks off the whole linked list process. This is the so-called root. All right, here I am at the number 4. I want to find the number 5. What decision can I make when I see that I'm currently at the number 4? Just like the phone book from week 0. Where is 5 not? It's not to the left. And if I had built a little mobile here or something, we could very dramatically snip off this branch. This is like very low budget animation. These nodes could like fall to the ground, and we're left with half of essentially a tree. But what do I now know? It's obviously the 5 to the right. So let me go to the right. 6 is obviously not the one I'm looking for, but what do I now know about the 5? Well, 5 is less than the 6. So I can sort of snip this off here because I know it's not going to be down there, and I can follow the remaining arrow here, and voila, I just found it. And now without getting into the weeds of the math, I've got here, 7 elements. That's roughly 8 if I round up. And if I do some log base 2, 1, 2, 3 is the key detail here. The height of this tree is 3 because I took a list of size 7 and I halved it and I halved it in order to let it dangle in these 2 dimensions, plus or minus 1 for rounding's sake. So what do I get back? I now have binary search, but it's not like the middle of the middle of the middle. I now follow these arrows in one of 2 directions. So each of these nodes now has an int and maybe a left pointer and a right pointer, but you could call them anything you want. And so I've gotten back binary search and dynamism, because if you want to add 0 or 8 or 9 or 10, we can just dangle them at the bottom of the binary search tree. So what would this look like in code, but we won't actually implement it line by line? Well, here was previously our definition of a node for a linked list, which was one-dimensional, if you will. Even though it might bounce up and down on the screen, it was still just a line, if you will. Well, let me get rid of the single pointer in the linked list. Let me make a little bit of room here in this type def, and let me propose that we just add 2 pointers, each of which is a struct node star. One will be called left by convention. One will be called right by convention. And so long as someone, not me, not today, not in class, writes the code that stitches together this data structure too, handling both the left child and the right child, so to speak, I think we can indeed stitch together that 2-dimensional structure. And moreover, once you have this in memory, you can translate pretty elegantly to code binary search itself using a principle we talked about recently too. Here is, for instance, a function that I'll write by just clicking through steps called search, whose purpose in life is to return a Boolean, true or false. The number I'm looking for is in the tree. This search function, therefore, takes 2 arguments. The number I'm looking for, called number, and then a pointer to the tree, the so-called root of the tree. Now, how can I implement binary search in code? Well, recall our brief discussion of recursion. It turns out recursion is a beautiful technique, and honestly, more obvious technique when you have 2-dimensional structures, which finally, after 5+ weeks, we now do. Here's maybe my first line of code here. If the tree is null, then obviously return false. You've handed me an empty tree. There's nothing going on. Obviously, the number you're looking for is not going to be here. So that's my safe base case to make sure I don't screw up and recurse infinitely. Well, what else might be the case? Well, if the number I'm looking for is less than the tree's own number. And now recall that tree is a node star. So even though I'm calling it a tree, it's really the current node that's been passed in. So if the number I'm looking for is less than the current node's number, then I must know that the number I'm looking for is to the left, so to speak. So how can I solve that? Well, this is where the magic of recursion. Just return whatever the answer is to calling search again, but on a subtree, if you will. This is the sort of equivalent of snipping off half of the tree. Pass in the left subtree, if you will, with the same number. Else, if the number you're looking for isn't less than the current node's number, but greater than, snip off the other subtree instead and just return whatever search says it finds in the right subtree here. And then there's a fourth and final case. What else could be true logically? Yeah? Perfect. If the number you're looking for equals the number in this node, then I'm just going to return true. And you might recall from our recurring discussions of design, I don't strictly need to ask that explicitly. Either there's no node, it's to the left, it's to the right, or you found it. So I can just whittle that down as usual to an else. And this now returns my true. So here too, this is where recursion, once you get comfy with it, sort of gets pretty elegant and cool in the sense that, wow, even though there's a lot of lines here, I mean, there's only a few interesting lines. A lot of it's like curly braces at that, which strictly speaking I could get rid of. And so recursion lends itself to elegance when it comes to traversing these two-dimensional data structures as well. So that is in code how you might implement something like search. Questions then on these trees? We have dynamism. We can insert more nodes to them. They're faster because we get binary search back. But there's got to be a price paid. Any downsides or question or downside? OK, let me come back to that in just one sec. Downside, though, what price have we paid for this dynamism and for this binary searchability? Even though I've abstracted it away in the picture. Say again? We're using a lot of memory, right? I'm kind of misleading you now because I'm just drawing these little squares with the simple numbers. But there's actually 3 things in there: a 4-byte integer, an 8-byte left pointer, a 8-byte right pointer. So we're already up to 16, 20 bytes now to store individual ints. That's probably OK, though, if memory is relatively cheap and voluminous as it nowadays is. But these are the kinds of trade-offs. And here, too, you see a hint of why some people still do like and use C. And in fact, it's so omnipresent because when you have C, you can really fine-tune how much memory is being used, for better or for worse, under the hood. As we transition soon to Python, these decisions get made for you. And you have much, much less control about how much memory is being used by your program because someone else made those design decisions for you. Question? Is it bad if we don't know the parent node? Not necessarily. There's no reason why you need to have pointers in both directions. However, that can lend itself to efficiency. By spending more space and having arrows go up too, you can actually save more time when searching the tree in other contexts. This, though, would be the canonical way, the typical way to implement it. But absolutely, just like a doubly linked list, that could help you solve other problems too. All right, so turns out I'm kind of overselling binary search trees. There are perversions of them, so to speak, whereby they won't actually behave as advertised. For instance, here's a good situation. Suppose you've got an empty tree initially, and you insert the number 2. Well, it's got to go somewhere, so it might as well become the root of this binary search tree. And let's assume that someone wrote the code to do this. Now you want to insert the number 1, and you want to maintain the searchability of this tree. Well, it's important to note that binary search tree is different from tree. If you've just got a tree in memory, there is no social contract with where the numbers need to go. They can be completely random all over the place. Binary search tree means that you can do binary search. Means that any node here is going to be greater than every node here and less than every node here. And that's a definition. It's a recursive structural definition that must be true to be a binary search tree, or BST. So if we maintain that property ourselves, let me insert 2. Let me insert 1. 1 belongs there by that definition. Let me insert 3. 3 belongs there by that definition. But I kind of got lucky in that I, in the story, inserted 2, and then 1, and then 3. Let me propose a sort of perversion of the algorithm whereby we just get unlucky. Let me propose that we insert 1 first. And then we insert 2. Well, where does 2 go? Well, logically, it goes to the right because it's larger. All right, now the user inserts 3. Where does it go? OK, it goes there, logically. And how does this story unfold? The user inserts 4, 5, 6. It's wonderfully sorted in advance by luck. But this is a perversion of the structure in what sense? It's still technically a binary search tree. But what does it look more like? It really is devolving, if you will, into a linked list. And so if you, the programmer, don't implement a binary search tree with some kind of repairs going on, such that as soon as something gets, whoa, a little too long and stringy, I think I can fix this. It's going to be an annoying number of lines of code, which we're not going to write here or in a P set, but we could kind of pivot this thing, right? And we could just rejigger things so that the 2 becomes the new root, the 1 becomes the left child, the 3 becomes the right child. But that's what, like 2, 3 plus lines of code. It's possible, it's doable, but it's extra work, it's extra code. So unless you write that code, though, and maintain balance of these trees, just because it's a binary search tree does not mean its height is going to be log base 2 of n. The height could be n, in which case you don't get those properties. So when it comes to looking up in a balanced binary search tree, yes, it's log n. But if it's unbalanced, if you don't add that additional logic and those repairs, so to speak, it could devolve into big O of n. And this is a whole category of algorithms and fanciness that you would explore in a higher level course on algorithms and data structures. There's lots of way to do that sort of fixing that I'm alluding to in the picture there on the screen.